So the plan is to do some examples of Morse homology and also talk about the relation with cellular homology. And it's useful to have the relationship. It's useful to know that Morse homology means the same thing as all the other homologies, because otherwise, saying look, we have straight proof of Poincare duality doesn't seem so impressive, because it's sort of Poincare duality is sort of totally obvious in this case, and so saying straight Poincare duality is obvious. It's not that exciting. It's not the same as something that's hard to prove in another theory. And so I think some examples are lacking, and maybe we should do some simple examples first, which will lead us to seeing the relationship with cellular homology as well. I just haven't done these examples. Maybe they're obvious to you, maybe they're not, but it never hurts to do something slow and careful. Let's start with, let's just start with that. So let's start with one dimensions, just to be really simple, right? So you can have a circle as one, a standard Morse function which has a single index 0 critical point and a single index 1 critical point, right? And then C0 is, C1 is P and Q, C1 is generated by Q, and C2 is generated by P, C0 is generated by P, and that's all there is. And the boundary of Q is equal to, well, what is it? Well, okay, that, of course, right away you're too low of a dimension to make good sense of intersections with signs, right? But you have to orient. Well, what do you have to do? You have to orient the descending manifold for Q. Okay, so the descending manifold is actually everything except P, right? So you orient it, let's say, this way, for example. And then you have to orient the ascending manifold for P, which you could also orient the same way. And then you have to look at a level set in between them, which is 2 points. And you have to count the intersection of the descending manifold, which is these 2 points. So anyway, these 2 points will be oriented with this. Anyway, so this case, yes?
In this particular picture, if you choose an orientation for the descending one, isn't that giving the orientation for the ascending one?
I want to say that you can choose those orientations independently, because if you
two
switch,
different submanifolds.
there are 2 different submanifolds that happen to coincide in this case. Well, there are 2 different codimension 0 submanifolds that happen to intersect along these 2 open arcs. And what I like to say is for each critical point you choose the orientations, and it doesn't matter. There's no compatibility condition from one critical point to another that you need to tell. If you switch the orientation on one, it should change the signs of both of these, right? And so, anyway, there's 2 points. You figure it out. Somehow you get a plus and a minus, right? In this case, the whole issue is how you orient the middle level set and all that. But anyway, therefore the boundary of Q is just 0, and the boundary of P is 0, and so therefore the homology is the kernel of the map from here to here is the whole thing, and we always have 0 coming in, so H1 is just Z, and H0 is Z. Okay? Let's just do it a slightly different way, just to that's generator one. Okay, now we have V1, V2, V3, Q1, Q2, Q3. And now what's going to happen is that the boundary of Q2 is going to be equal to, well, again, in this case, the signs shouldn't really matter. It's going to be, because it's going to be P1 plus P2. We're going to have a flow line from here to there, and a flow line from there to there. Boundary of Q2, that was Q3. boundary of Q2 is going to be equal to P2 plus P3. And the boundary of Q1 is going to be Q plus P1. And then it should work out that the kernel is generated by Q1 plus Q2 plus Q3. And so we have, because if I take Q1 plus Q2 plus Q3, all I'll do is I guess I probably do have to be careful about signs, right? If I look at these points of intersection, I didn't even draw it as a self-indexing critical point. I'm using that. So I really should take a level set in between everything, that, right? And these signs should, these should come, I should choose a solution minus plus, minus. And so then this would be P1 minus P2, this would be P2 minus P3, this would be P3 minus P1. That's the kernel of the boundary map is generated by Q1 plus Q2 plus Q3. There's no image, and so we can work out that's what we get. So, and then of course the image of the boundary map is 0. What am I trying to say? The image of the boundary map is not 0. The image of the boundary map is going to be, so that tells you that H1 is Z. There's only one boundary map we're looking at here. And if I want to know the image of that boundary map, well, it's generated by these three vectors, but we can pick out something that's spanned by, what is it spanned by? Yeah, any two of those will do, right? So spanned by the image of the boundary map is spanned by, it's generated by P1 minus P2, P2 minus P3. With those, you can get the other one, and that's two-dimensional, and you figure out that's inside subgroup spanned by P1, P2, P3. The kernel of the outgoing map is everything. So, well, naively, this is three-dimensional, that's two-dimensional. The kernel is, the quotient is one-dimensional. That's not quite enough. You know, there's no torsion, but you can figure it out here. Generated by any one of those. And this is somehow also should be consistent with the top dimensional homology is sort of generated by the whole manifold, right? So sort of the top dimensional homology is generated by the sum of these, you flow down and get everything, right? And then the zero dimensional homology is generated by a point. Any point is as good as any other point. So that's sort of why it's Z generated by any one of those. And that's sort of, that you should see that happen in general. In fact, probably you can, for any closed manifold X with a Morse function, X in N with a Morse function F, the top dimensional homology of X is equal to Z generated by the sum of all the critical points of index N. And the lower dimensional homology is equal to Z generated by a single critical point in index 0.
Connected or interval?
Yeah, connected, connected, closed. Oriented is needed to make this work over Z. The same statements are always true over Z2 if you remove oriented. So then it's not Z, it's Z2. And of course, one thing we know is that you can always find a Morse function such that you only have a single minimum and a single maximum. We already talked about that, in which case this statement's trivial. But the claim is if you pick one that has more maximum and more minimum, this claim would work as well. So let's see. Here we're going to get, to understand why this is true, we want, well, let's do this one first. If I look at the top dimensional critical points of top index, I want to understand flow lines from them down to critical points of index 1 less, right? So I can momentarily turn things upside down. I'm looking at flow lines from index 1 critical points down to index 0 critical points. And index 1 critical points always have two descending manifolds, and they'll always intersect they'll hit, one of them will hit one index 0 critical point, one will hit a different one, but they're always with opposite signs. So looking at it this way, it'll tell you that the boundary of, you're always going to have the situation where the boundary of each maximum index critical point is either 0 or it's it's a sum of plus or minus of two of the index n minus 1 critical points. So it's going to look exactly like this, and therefore the kernel of that map is going to be precisely the sum of those critical points. On this side, for the index 0 critical points, you then look at the boundary of the index 1 critical points. But again, now each index 1 critical point flows down and hits two different index, possibly the same index 1. Well, you want to know about the image of the map, right? So it's going to hit, maybe let's talk about this more carefully. So you want to think about the boundary from C1 to C0. C0, let's say, is generated by P1, Pk, and C1 is generated by Q1 and QL. And the boundary of each Qi, there's two possibilities. Either there's two flow lines that go to the same critical point, and they'll be with opposite sign, so they're going to be 0, or it's equal to some P, PS minus PT for some S not equal to, well, I guess I could collapse those in the same cases, right? And then I want to know that right, so then I claim that the image of it, the image is just the sum of those, right?
They pair up.
They pair, well, what we really, you really need to know they pair up to generate something with one less dimension, right? The first thing is that, say P1 is not an element of the image of this boundary map. So it can be taken to be, and I want to claim that, so it certainly represents a non-zero class in H0. So in other words, there's no way you can take the sum of things like this and get, every element, therefore, another say is every element in the boundary of Qi sort of involves an even number of things in C0. Because you're not going to, if you add this to some other PT minus something else, you're still going to have two terms, right? So you're never going to have a single thing. And now I want to say that the second thing is that for all j not equal to 1, P1 minus Pj is in the image of the boundary map. That would show that Pj is equal to P1. Now that's not completely obvious from here. What you need to do is you need to get a path. You need to find this sum of 1 handles, index 1 critical points, that adds up to P1 minus Pj. So you need to go P1 to, you basically need to find a path of 1 handles that goes from so you think of your index 0, here's P1, and here's Pj, and you're going to find some other things so that you've got an index 1 critical point there, and an index 1 critical point there, and an index 1 critical point there. Now, if such a path does not exist, then that's going to mean that your manifold is disconnected. Because the only way to connect up to index 0 critical points, if your index 1 critical points don't do it for you, you're not going to be able to do it with higher index critical points because they don't connect disconnected things. So if you ever cannot connect, if you cannot find a path from P1 to Pj, in the union of the zero and the index 0 and one critical points in the descending manifolds, then you have no joint open making it connected. So connectedness tells you can find this path, and then that tells you then it's the sum of these critical points between one and two. That's any questions on that? Again, that's a fact you probably already knew about homology, but it's and not just the statements what they're isomorphic to, but what they're generated by is carries a little bit more weight meaning there. Of course, I could also just use quantum duality, because I could have said H lower n is isomorphic to H upper 0, and H upper 0 is just the thing you get by, no, I guess that doesn't quite follow. Okay. So let's do a two-dimensional example. Again, we'll start with a simple one. Let's do. That's straightforward, right? Index 0, index 2, there's not even any index 1 things. So anytime you have a missing, you have 0 goes to Z, goes to 0, goes to Z, goes to 0. This is C2, C1, C0. So that immediately tells you that homology H0 is Z and H2 is Z. H1 is 0 and H2 is Z. Any questions on that? Maybe we'll just throw in one where there's we'll do S2 one more time, but with some index 1 critical point and index 1 critical point. P, Q, 1, 2. Let's quickly check. So now C2 is on here again. So C2 is generated by R1, 2. That's 0 mapping into it. Mapping to C1, which is generated by Q. Mapping to C0, which is generated by P. Mapping to 0. And actually, let's just write the boundary maps as matrices. This is just the 0 matrix. And this should be a 1 by 2 matrix. And so the boundary of R1, so we're going to take the ascending manifold for this, oriented saying this way. And then the descending manifold for this, oriented so that, say, that goes that way. And then in here we have a sign. Well, actually, in this case, the sign is really not going to matter because we can choose those independently. And so this could be, but there's one point of intersection, which is say 1, 1. And so the point is now, yes, C1 is in the kernel, but it's also in the image, right? So the kernel of this 2, kernel of boundary 2. Is generated by Q, is the whole thing, but the image of kernel of boundary 1, the image of boundary 2 is also Q, because each one of those maps to Q, and so therefore H1 is still 0, and H0 is 0, obviously, and we have Z, and for H1, well, we have 2 generators now, but the only thing that's in the kernel is the, that's what we said before, it's R1 plus, well, that now, I said it's the sum of them, right? That with certain signs, I guess I should have, if I had oriented it, say that's minus 1, depends on how your orientation, if I flip the orientation on this, then I have to flip my generator, right? So this is really sums. And it doesn't matter here, and again, you get these 2. Now we'll just do that. torus. So okay, when you first see a picture of a Morse function, I never do this, I was bad. You see there's your torus, you go with the height function, and I've got my index 0 critical point, I've got two index 1 critical points, P1 and P2, and I've got my index 2 critical point R, and remember, if there's two flow lines from there down there, obviously. You might, if you draw this perfectly symmetrically, then you get flow lines from Q2 down to Q1, which is wrong. It's not generic. You tilt it a little bit, and they'll miss somehow. And then here you have exactly the same thing going upwards as well. Something like that. And so, again, the point is now you have R going to Q1, 2, going to P, but now all the maps are 0. Because they're always pairing off with opposite sign. Two flow lines, two flow lines, two flow lines, two flow lines. And so all the maps are 0. And so you get H2C, H1 C squared, H0 equals 0. Okay, I'm kind of rushing through it because I think this is sort of easy for you, but tell me if it's not. Okay. But just to clarify that things work. And of course with higher genus, the same thing will happen. You stack these up. But the point is, all you have is the index 1 critical point, so they just flow all the way down. And why do you get Z2 for something non-orientable? Well, first of all, you can't, the orientation is a problem. Well,
You mean for topology?
yeah, I mean, for the top dimensional. What I want to say is when you attach a 1 handle, right, then you have, there's an orientation flip on one side, right? So you sort of get boundary of something equals twice something else, rather than 0 counted on one side. Let's move to just a couple of, let's do lens spaces now, the 3 manifolds, and so this is sort of, we're going to work backwards. We're going to, there's a description of a lens space, which is, there's a lens space LPQ. It's a certain 3 manifold, which has many different descriptions. But one way to describe it is it's the union of two solid terms. And so they're going to be A and B. Here's a solid torus, A, here's a solid torus B. And let's see. I may get the convention. Right. So I want to do it. I'm going to glue these two solid tori together. And what I need to do is specify the image of. So P and Q are two relatively prime integers. So I'm going to glue by a map, say phi. Phi is a map from boundary B to the boundary of A. And this meridian over here, I'm going to specify the gluing by saying where phi of the meridian goes to. So this solid torus A, I can parameterize its boundary torus, with a sort of here I have two different directions which I can X and Y. So I can parameterize the boundary torus in this way, X, Y, and then the PQ is going to be used to define a slope, a line of slope, which eventually comes back to where it starts, of P over Q. That's the slope. Y equals P over QX. Now whether I've got P over Q or Q over P, I don't care. There's some convention as to how things work, but the point is, because they're relatively prime, then if you go P times around one and Q times around the other direction, you get where you started. You have a simple closed curve. You don't go around multiple times. And then the phi is determined by the fact that phi of mu equals this P over Q curve. now what I want to do is use this to compute, I want to use this description to construct a Morse function with gradient descending flow lines, etc., and count and compute them all. Everyone understand this description I'm giving? The first thing is why is that enough to determine the manifold? Just knowing where the meridian goes does not completely determine the map from the boundary to the boundary. And there are many different choices still for where the longitude can go. However, if you wanted to describe the three manifold, that's all you need, because you can think of, we're going to build the three manifold in such a way that A is the union of the 0 and the 1 handles, and B is the 2 and the 3 handles. So I want to, this description, this case, hammer body decomposition. Q, A equals a 0 handle, union, a single 1 handle, right? So A is a solid torus, so just a ball and a single 1 handle. And then, so we'll draw, remember, again like this. And now there's a single index 0 critical point, say here, and index 1 critical point there, right? So this is the ball, and then we attach a 1 handle there, and the ascending manifold for the index 1 critical point is then like that. So this is the ascending sphere, or the belt sphere, for the 1 handle. And then, well, B is going to be the 2 handles and the 3 handle, the 2 handle and the 3 handle. I'm just really reminding you how Hagar's things work. And so, but of course, you turn it upside down and it looks just like A. But the point is then, if you turn it upside down, there's a 0 handle and a 1 handle, and the ascending sphere for the 1 handle turned upside down becomes the descending sphere for the 1 handle. And so, basically, phi of, so mu is the descending, mu equals the descending sphere, which is just a circle, descending S1 and the 2 handle, and phi of mu equals the attaching, the image of the attaching map, right? The attaching S1 and the 2 handle. And so we draw it in here, and that's our beta curve. Well, now the key thing is we're going to try and what we want to do now is figure out. So here's phi of mu. It's not winding around some number of times. What do we need to know in order to compute the boundary map now? We want to know how many flow lines there are. Well, what do we know about the boundary map? Let's do the easy part first. The boundary map is now going to have, the chain complex is going to have everything equals Z. C3 equals Z, C2, because there's just there's one index 0, one index 1, one index 2, and one index 3. C1 equals Z, C0 equals Z, generated by the critical points. In this case, there's a single, we know that this map is the 0 map, because it's just one index 1 critical point, and it's got 2 flow lines down. And similarly, we know that this map is the 0 map because there's the index, going upwards, turning it upside down, there's one, it's exactly the same picture. Okay, only 2. Those flow lines are right there, right here, and right here. So there's 2 of them, they can't count the opposite sign. The only thing we need to know is this, which means we need to know how many flow lines there are from the index 2 critical point to the index 1 critical point, which means we need to count the intersection in the middle level set of the ascending and descending manifold, which is precisely the intersection of this blue curve with the red curve. And that's all we have to count. And then the question is, how many times around does it go? Well, maybe the best way to do is look back here in this picture, and our blue curve, the way I drew it is, the red curve is this. That's sort of the x-axis, so that's this. and the blue thing is this thing. And so the only question is, does it intersect p times or q times? So if it's slope p over q, what does that mean? That means as it goes over q, it goes up p, right? So if it, let's do the simple case, if q equals 1, then it's going to be steep. P is large and q is 1, it's going to be steep, so it's going to hit here p times. And if q equals, say, 2 and p equals 1, it's just going to hit here 1 time. So actually the p is the only thing that matters in this homology, and the boundary map is plus or minus p, depending on the orient basis in that matrix P, right? And so now we have H, of course, H3 equals Z, H2 equals H0 equals Z. We have that H1 is the kernel of this mod, so that's H1 equals Z mod PZ. And then H2 is, well, what's the kernel? The kernel is nothing, right? Everything goes to something non-trivial, so H2 is 0. The interesting thing about this is that, if you haven't learned this before, is that you can actually, this is, it's actually pi 1 is Z mod PC. Hard to figure out. And so, I mean, there are things that would be really nice Z mod PC that are not Z mod PC. In this case, it's just that. And these are maybe some of the first examples of manifolds that were had the same homotopy type, but were not necessarily homomorphic. And the question is, how can you then? What does Q have? It looks like Q doesn't matter at all, but actually there are LPQs with the same P and different Qs which are not homomorphic, and that was sort of a big. I guess Reidemeister did that, and invented something called Reidemeister torsion, and it's quite subtle. I mean, it's souped up algebraic topology, but it's pretty interesting how it's sort of the action of pi 1 on things.
Can we
Yes, go ahead.
do T3 or is it?
Yeah, T3 we can do, and T3 is not as hard as you would think, really we just have to draw a Haygarth split T3. That's actually kind of
That's my question. I don't know.
That's your question. Okay. So I'll show you how we actually I won't quite do it that way. So we'll do T3 as a box, a solid box with opposite faces glued. And now I want to show the 0 handle, 1 handle, 2 handles, and 3 handles. So this is an attempt at it. So the best way I know to do this is to chop this box up into, chop each edge into thirds. It's not quite symmetric, but okay. Slice it up into Rubik's Cube pieces, and actually, when you take a Rubik's Cube apart, right, there's the thing in the middle that looks like this. And then another one goes out front. Another one goes behind. Another one to the right. That you know what I'm doing, right? I'm taking away, I'm looking at the middle cube and then all the ones that touch it along the whole face, right? And I notice that actually is, that thing is a handle body of genus 3. I don't know if you can see that. So take the middle cube so the way it's going to work is the middle cube is the 0 handle. Then there's a 1 handle, right? I take the middle cube and I go out this face and connect to the face on the opposite side, come back in. That's a 1 handle. Do the same thing on the top, that's a 1 handle. The same thing on the front to the back, that's a 1 handle. So that's a genus 3 handle body. Then now by symmetry, the other thing, well, it's not, what you need to know is to know the other side of the handle body. Now, it's, the way I drew it, it's not quite symmetric because they're sort of bigger pieces, right? But the 8 corners all fit together into one block. And then there, so I take, and then going across here is a one handle, connecting this corner to that. Going across here is a one handle. And so that gives another genus through handle body. Now what you want to do is see where are the attached ascending, descending spheres. So now we know that for any Haggard splitting, we're always going to have 0, 0, and then some number of generators here, some number of generators here, and some interesting map here. So we'll see if we can figure that out. Of course, we know we'll see what we get. We already know what we should get. Should get a z cubed in the middle. So let me actually try to draw this thing that I was trying to draw here a little more carefully. And actually, maybe the way to do it is to just try to draw this in the front now. That one I know should be completely visible, right? Then this one to the right should be completely visible. So here should be visible. And now we can put one here. Let's see. Okay, good. Now, where are the alpha curves? Okay, so in the middle is the 0 handle, which we haven't drawn. Here's the 1 handle that goes out this way and connects to that side. So there's the belt sphere for it, which it also happens to be over here, but I won't draw it. Does that make sense?
Yeah, it's 2 more of those.
And I got 2 more of those. So there's one here, and there's one here. Now, where are the beta curves? Well, beta curves, so now we're going to think about putting, what are the 2 handles really? So there's a block to put in here, 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 and back there. When I put those blocks in, so when I put those blocks in, this block there, actually this side of it going to that side of that block there. And actually they all meet together along this edge, and they actually are a 2 handle. So I claim that maybe I can draw those lightly in yellow or something. I claim that those yellow pieces, if I take them off and reassemble them by fitting it faces to faces, will fit together into a piece like this. So label them and say this is, I'm taking them and turning them this way, so that's probably here. That's A. Put it down here, take it off and put it here, and then I take this B and it goes over here, right?
The
Take
outside
B and
faces.
put it down here,
Yeah,
and then what fits above A is this thing C, and what fits down is that B, right? Does that sort of make sense? So that's the yellow thing that's fitting around, and now where it's mapping in, where is it lining up with what I've already got? It's lining up with what I've already got on this outside. So that's the sense in which it's a 2 handle, and here's its descending curve, which when I draw it here goes there, up, continues here, there, continues back, which you can draw, back here, back there, back, I think I've drawn enough of it, right? The point is it has 4 little segments like this. But again, the point is it's going to intersect each alpha curve in 2 points with opposite sign. Well, that's actually worth checking. When it goes, let's just check that sign. So it goes up here, and now we want to know that it's going up when it comes back there. So it goes, follow the arrows backwards.
Physics right.
No, what am I doing wrong? That's right, no, we want it to be going the opposite. It comes in here, so it's like John Carrier. Somehow I can't follow it, it's backwards. So I orient it this way, and then it comes this way and goes up. And so it's crossing here with opposite signs. So plus and minus. So therefore, the boundary of these two cancel, and the same thing will happen symmetrically everywhere. And so we have the chain complex, which goes z cubed, goes to z cubed, goes to z, 0. That's the chain complex because it has 3 index 2 and index 1 critical points, but all the boundary maps are 0, so that's the homology as well. Okay, that makes sense? Okay. Maybe the last example I'll do is I won't even write this down. There's a standard way to write down, actually explicitly in coordinates, write down a Morse function on the complex projective spaces of CPN for any x. And maybe I don't want to write it down because I screwed up because I didn't compare it. But I'll try, maybe let's try to remember for next time. As a Morse function, you can write down completely explicitly and compute index and so on. And it has critical points only at even index. It has 1 critical point in each critical points only at even index. And exactly 1 in each index. 1 in each index. So, what does that mean? That means right away that your boundary maps are all 0, because you go z 0 z 0 z 0 z 0, and it tells you the homology therefore is equal to that chain complex, so that tells you its top dimensional homology is 2n, right? H2n equals z, and equals z is even, 0 gives up. Yeah. Oh, first one's bigger. And 0 for k greater than 2n. Okay, so I want to start and next time finish the claim that this Morse homology, Morse complex is the same as the CW, the cellular chain complex for a particular CW complex decomposition of the manifold. There's actually 2 things you can do. One is to prove that for a closed manifold, the Morse homology, the critical points together with descending flow lines gives you a CW complex that is homotopy equivalent to the manifold. A little bit harder to do is show that for a closed manifold, so that's true for any coercive, what I would say. Then for a closed manifold, you can show that the manifold is actually homeomorphic to this particular CW complex, and that's a little bit harder. And I'm not sure if I'll do that, but let's start with the easier one. So the first claim is that if x coordinate from 0 to 1, let's go back to the very basic case with exactly 1 critical point. Within a Morse function with exactly 1 critical point. Let's say P, then X deformation retracts onto N0 union the descending manifold for P. and that is, and the descending manifold for P is actually a disk. So this is which equals M0 with a cell attached, a K cell attached. K cell just means a k-dimensional disk attached, where K is the disk. Well, it's not really that hard to see. First, just the picture, right? Zero and one, and so here's the critical point P, and here's its descending manifold. Remember, in this case, well, there's sort of two different cases whether M0 is empty or not. That's the case where M0 is not empty. Then the descending manifold, there's no other critical points. So the descending manifold is actually compact and actually goes all the way to M0, and that's it. And so we just have to see the deformation retraction. That's the picture. Now, to actually write down that deformation retraction is a little, what you want to do is you want to sort of flow along the gradient vector field, right? But it's a little fiddly because if you flow along the gradient vector field, you, first of all, these points flow for infinite time. What do you want? You want some one parameter family of retractions so that in the end the whole thing is mapping onto this union this. And so you have to figure out how to, if one thing you might be tempted to do is to say that the deformation retraction is going to be, you take a point and you flow along the gradient flow line, right? Descending gradient flow line, and you either flow for infinite time and then take the limit if that's, if you have to, or else you flow until you hit the bottom. The problem with that is that's going to be the entire, that's going to be very discontinuous because take a look at these two circles up there, right? These 2 points on the circle are going to map to here, and everything else is going to get mapped to the bottom. So you have to kind of make some interpolation between, once you get into a sufficiently small neighborhood here, you have to change your flow so that you actually do end up limiting on this picture. But it's a lot easier if you already believe that in Hammond decompositions, right? Because the point is, if you already believe that X is diffeomorphic to M0 cross M01 cross M0, union two handle, which is sorry, a K handle, union BK cross Bn minus K, with attaching that phi, then the deformation retraction. So first you just retract in the direction of the Bn minus K, right? So you just do the retraction in 2 steps. So this retracts onto 0, 1, cross M0, phi. Well, actually, you have to be a little bit, you still have to be kind of careful. 0. Because if you're attacked, even if you see this even in this case, so we're going to say this thing retracts onto my handle on that, right? And so this thing is diffeomorphic to this. Now I want to retract just onto here. And again, once it's fine to retract there, that's fine, but once you get down here, you still have to be a little fiddly and do your retraction kind of carefully so it's continuous, otherwise, should that point retract to there or not, but I won't write that down, that's all sort of, it's all just in local charts, and this picture does capture everything that happens. And then once you have this, then that you can retract from the bottom up, or however you want to do it, that definition retracts from 0. Let's say. So now once you have that, then what you would like one way to do it is to sort of, we don't have enough in this simple case to talk about the cellular homology yet, because you need more critical points to interact. But this is going to be, basically, this way of doing it in terms of deformation retraction allows you to more or less build things handle by handle and do an inductive proof that we have the same homology, which is a lot easier. And so we'll see what I'm prepared to do next time.
So it's tempting here to try to say something like, sort of start with a simpler claim that's if you have no critical points,
That's right.
then you sort of can
Retract on the
retract through the cylinder.
That's right, which is true.
So then, then it's almost like you'd want to say on the right here, I sort of have a cobordism between like a piece of M1 and like this thing that's not in a manifold. It's like just
Yeah, right.
like this right half of M0 along with the descending manifold.
Right.
So, but that's not a cobordism between
Right.
two manifolds.
That's
it's
right.
like a
Yeah.
cobordism between a CW complex.
That's right. And you could try to cook up such a theory, but I think it gets, you don't have colony or
But it's not easy.
so yeah, I don't think it'll help. The point is, another way to think about, attaching a handle is like building a CW complex but thickening up to be a manifold. Right? That's the whole point. You want to stay in the world of manifolds. So you don't just attack an arc, you thicken it, and then it's a manifold, right? So it's